Have you seen the water refill station?
I think it's better that works.
I'm normally at the table.
Like halfway down this hall, there's like a little like inn. It has some bathrooms. There should be water fountain somewhere. Do you by chance have Verizon? What? Are you carrying on Verizon wireless?
Unfortunately. Fortunately, but unfortunately.
Yeah. You probably heard about that. There's like a national Verizon outage. Nobody can call or text or
Yeah.
do anything without Wi-Fi right now. So.
Wi-Fi?
No, I have it in here. I just like, I went to go pay for my parking. And I'm like, oh no, I have to park and go all the way inside and like pay for it there because there's no like actual manual ticket thing.
So used to the, whenever it goes on, there's free parking. So I got so used to free parking. So I parked this morning and came inside and then I got out of my car and saw a parking ticket and went,
No, it's for anything regular, like
Redwood Table Rock, all free parking this year. I've now spent $45. I just spent $45. Bought myself lunch and then I had a parking ticket. So.
I usually go to the library parking lot because the first hour is free. And I go to the one that's over, you're walking towards that. It's for like
I'm here all day on Mondays. And this morning I'm doing just payroll and parking. So I'm letting them move my car every day. Because I feel like I'll end up spending that amount of money in gas.
I saw people posting online, but I actually have Verizon and I have like bars. I don't know. But I did see other people like talking, asking if their Verizon was acting up. Bless you. Yeah, we can do that. Yeah, and I'll talk about other stuff that I do, because I actually stream a lecture live, so I don't know if that would be easier for you, if you're just on lunch break on Wednesday.
Yeah, it could be.
Yeah, I was just showing the thing about,
Okay, is that something you would want me to log in and watch live Zoom?
well, I actually do it on YouTube, but yeah, we can talk about all that. Yeah, I think we can do that, but, yeah, if we do that, I would say, you know, be proactive, find me for the office hours, ask questions.
Your office hours are on the syllabus, right?
I don't know if they're accurate, but
I'm on it now.
I'll talk about office hours and stuff.
Yeah, I'll be able to do the quiz and class this week, and then after that, it's gonna be all.
Okay, yeah, we'll figure it out then. Recitation is just like time set aside to basically go over stuff, but I use it to review and also get quizzes. So you have to sign up for this.
And the registrar.
Oh, yeah, like how we register for classes. It's on Wednesday from 2 to 3. So the idea is it's supposed to be block scheduling. Monday, Wednesday, you have classroom 1 to 3. Both days of the recitation is during that period.
I signed up for this class and had to switch last minute.
Mm.
This class was like, the last class, so it was really like, I didn't get anything else, and then most of the last ones that were really tall, so.
Yeah, I haven't like, I didn't really email do that because I assume people are coming in and out, but yeah, we just gotta get everybody signed up for lab lecture recitation, but I'll go over all that. All right, let's go ahead and get started. So first I'll call roll, and obviously I'm only going to do this the first day, and if you go by another name or I totally butcher it, just let me know. Taylor Bishop. No Taylor? Okay. Kaylee. Giselle. Okay, you're in lab. Michael Bowling. Excellent. Braden.
Present.
Crystal Cortez. Rebecca's here. Kelsey. Kelsey Duarte. Okay. Marin. I almost screwed up your name again. Catherine was not in lab and did not make it, apparently. Madison. Angela. May. Sarah McMurtry. No, man, we're missing a lot of people. Brianna, you're in lab, you're here. Jubelinda. Last name, Molipola. No, man. Isaiah. Ellie. You're here. Noelle, you're in lab, you're here. William Wass. Okay. And Miracle. Okay. And then is there anybody who wants to be in Chem 104 who is not signed up? Okay, nobody lost. All right, so that being said, I'm a little disappointed we had so many people absent. Maybe they're not going to join us. So that being said, if you are in here, you need to make sure that you are signed up for lab, lecture, and recitation. So make sure you do that ASAP. And so there are a few of you I know who are not signed up. I haven't looked at the names more precisely, so maybe they're the people that are not here. But if I called your name, you're here, and you're not signed up for recitation, do that ASAP. And so all recitation is if you were to take this class at a university level, right, the professor would yak at you, and then later on you would go into like smaller classes called your recitation, and then there would be like a graduate student TA that leads that. So that's like the model that we're copying, and that's like why it is. And so kind of the thought behind it is that it's only for chemistry and physics that have recitation. And so that's, of course, they're very math-heavy subjects, so you have this recitation block as just kind of devoted as extra study time and just extra class time. And so the way I use it is usually we take our quizzes during recitation, and so it's on our Wednesday, but just after, our lecture, I tend to maybe lecture for about an hour, we'll take a break, and then we do a quiz. And then after your quiz, you can stay in recitation, right? That's your time to ask me questions, get homework help, do problems, yada, yada, yada. All right, so does that make sense for lab, lecture, recitation? And everybody should be in lab, so I think we got that sorted. Yeah. Oh, the recitation? Yeah, recitation is technically Wednesday from 2 to 2:50, but I just think of it, right, as we have Monday, Wednesday lecture, just from 1 to 4, essentially. Wait, is that right? 1 to 3, sorry. Keep you here for another hour. All right, so that's just considered our block time. And again, we just have that recitation as kind of a formal piece. All right, I forgot to introduce myself. So obviously, my name is Marissa Shepard. Email is the best way to communicate. Oh, what's your name that snuck in?
William.
Okay, William, nice to have you. And then, yeah, just try to get the class on time.
Yeah, apologies for that.
Although I will say the course messages in the new Blackboard actually ping me. So maybe your course messages will not go into the black hole. But like I said, email is best, right? I'm a millennial. I have my phone. I get a notification, so I can help you right away. Let's see, other things. So this morning, I think they were just slow to take down the fence. So now the bridge down there to the Almond Street is open. So check that out for free parking. And then, does everybody have RCC security in their phone? So yeah, probably not a problem for our class during the day walking over there, but if you have any night classes or see anything sketchy, don't hesitate to call security. And so let's look at our Blackboard. And so just a couple of things. Sorry, my Blackboard looks crazier. And so, of course, we have our lab shells and our recitation shells. I don't use any of those. So everything will just be in the lecture shell. So I'm trying to make things easier for y'all. But then the other thing is I'm going to hand you everything that you need, right? So you walk in the door, there's your homework, there's a lab if you obviously didn't have the Monday lab and didn't grab it already. But everything's there for you to grab. So there's nothing you need to be worrying about on Blackboard. And so that also being said, so I like to be accessible. And so I have this link here on the syllabus. And so this goes to my YouTube page, which I'm not going to open now because I'm live streaming. So I don't want to cause weird things. All right, person sneaking in, what's your name?
Kelsey.
Kelsey, all right, you've made it. Yeah. I think there was one extra, but you can grab it later because I added like a conversion cheat sheet for later. Yeah, so now we'll be meta. And so you can see, right, we're streaming live, and then there you can also see all our other past lectures, and I have some playlists, but again, you can explore that later, so that's helpful. And again, if you can't attend live, just go in the chat, say hello, so I know you're there. All right, then we have our syllabus, so blah, blah, blah. So things we should talk about. So this is the official textbook, but I don't really care what edition you get. So it's, I think in the bookstore too, they probably have a custom print book. That, yeah, I think do you have that custom print? Yeah, so you can hold it up. Yeah, so that's what the custom print looks like. That's just a certain number of chapters taken from this book and printed out for RCC. So you could buy it that way. Have you guys heard of OpenStax? So OpenStax is a great resource of a bunch of free textbooks. And so I say, like, maybe you're just kind of taking this class to take a fun class, which I know this is like a general science requirement. Maybe you don't want to buy, the textbook. I actually don't know what they go for. So this book is completely free. So you just go to openstax.org, and then they have so many books, but right, you go under science, find chemistry. So this is the Adams First, second edition. Obviously, it's not going to pair perfectly, but all the same information is there, right? We're just studying basic chemistry. It's basic information. You can literally find it in any Gen Chem textbook, basically. So, right, if you're not, married to the chapters and everything, feel free to get other resources. Everything's there. And I don't ever assign problems from the book. I don't really reference the book. So, right, it's not essential. But a great reference material, of course. But again, this is also great in a full Gen Chem textbook. Otherwise, you can search different editions online. I think this is like the current. Oh, actually, there's a newer edition. No, that's not the same. They're trying to confuse you. This is not the same book. This is a book, this GOB book. So it's called General Organic and Biological Chemistry. And I'm sure you can find, so notice, right, this is not the same book. That's just OChem. But yeah, it's this edition, but you can get, again, any other edition, whatever's cheap, or like I said, the free textbook. All right, so back to the syllabus and kind of how this course runs. So generally, right, we'll have our lecture on Monday. I'll hand you all your materials. And then basically everything is due next week. And so kind of, I'll write this out, kind of our typical schedule. if I could spell. So our typical schedule is that our homework will be due the week after. And I think I just set the due date to the Wednesday, so you could just turn those in. Again, it doesn't really matter. And then we will also have our quiz on Wednesday as well over, right, the previous week's topic. So this week, of course, right, we don't have a previous week. So our first quiz, so this week, so week 1 quiz will just be a welcome assignment. So we'll just kind of, practice how it's going to go. We'll have our 1-hour lecture. I'll hand out your little welcome quiz, which is just basically like, why are you taking this course? Something about yourself, like, something fun. And then next week, right, we'll get back into the rhythm. So next week on Wednesday, we'll have our chapter 1 quiz. And then labs 2 are due a week after. And so ideally, right, if you're the Monday lab, you'll hand it to me on Monday when you go back to lab. If you need an extra day or two, I don't mind. And if you're, again, the Wednesday lab, you need to finish up something, right, ask me questions and turn it in. And so I don't know if students gossip or whatnot, but you may have heard that I'm pretty flexible with deadlines, so I'll try to continue to do that. So basically, right, I just want things done ASAP. It is in your best interest to, of course, keep on top of your assignments. So generally, if students fall behind, right, they're not going to be successful. But I will do everything in my power to be very flexible and accommodating towards y'all, because I understand life happens. All right, blah, blah, blah. So yeah, we'll just kind of go through our chapters. And then, of course, exam, week 5. And so for that week, we'll review on Monday and then take our exam in class. And yeah, pretty much follows regularly. Other things to note, so week 7 is Columbus Day / Indigenous Peoples Day, so that does mess up our lab schedule, so just notice no lab on week 7. And we do have lab. I believe this is Thanksgiving week on the Wednesday. So if you are planning on traveling on that Wednesday and need to switch to the Monday lab temporarily, we could do that. So just kind of things to keep in mind. All right, any questions on that so far? Yes.
So is the lab for this to get, like, usually on Mondays? Because I send it for the Wednesday.
Yeah, so there's a Monday and a Wednesday lab. So there's 2 lab sections. I prefer that you go to your assigned lab section, but with this class, it's so small that if you needed to bounce back and forth, it's not a big deal.
Okay.
Yeah.
Is there anything we do need to study for this week's quiz?
Hopefully not with the welcome assignment, because it'll just be a welcome assignment. Yeah, so no studying. And then so other things that I put on Blackboard, and I apologize, so this is my first time in Blackboard Ultra, so I don't know how well everything copied. So if you go under content, here's some chapters for the textbook. So the first 4 chapters are there, available to y'all, and that's again from the GOB book / the RCC copy, they're the same thing. And then afterwards, you'll have to determine your resources for the rest of the chapters. And so I have chapter 1, I'll probably deploy chapter 2 soon, just to keep it open. And so I tried not to confuse you. So I have, the homework, the lab report there, but again, I'm handing you physical copies. So you don't need to go in here, you don't need to turn it in online. Does that make sense? You can, but I really prefer physical copies. And then this is where you might want to look at stuff. So I have my lecture notes. So I use a OneNote, and so I have this OneNote template, and you can copy it from here. And I forgot to do this, but I will post it shortly. And so later I'll post what's called my live version, so then it updates live, and you can have, the latest notes on there. So I'll put that up as a lecture note. So I have PDF, OneNote template of that, so if you don't have OneNote or it doesn't work, because it's a one package file, so it has to be the full like version of OneNote, not the app. So then I have the PDF. And then I also kept old lectures and references in there, so you know, if you want extra stuff to look at, it's all in there. So I think if you click on, yeah, on this, so this is other lectures from another instructor, again, if you want more resources. So I just kept it there for your pleasure. And again, I'll deploy more stuff. And of course, right, ignore your grade book right now. It's obviously a mess. And then probably when I set your grade book anyway, it's going to be on what's called like zeros. So basically anything that's not turned in will be a 0. So you'll have a scary 0 for your grade, but just don't panic. All right, any other questions or anything? Logistics? Yeah? Oh, once a week. Yeah, so again, just think about it as we have our block of lecture times, right? Monday, Wednesday, 1 to 3, so you don't really need to worry about the recitation part. So let's start diving into lecture then, unless we have any other, again, logistical questions. So what is chemistry? And so maybe y'all can tell me, or like, what are your interests? You know, why are you in this class? How could we relate chemistry to your interests? So what do we think about chemistry? You got to get used to all the sirens, you know. It's a common occurrence in this lecture. So yeah, what do we think about chemistry? You don't want me to start picking on people. That's really...
Chemistry is basically the study of formulas, I believe.
So you said study of formulas.
Formulas of how things occur.
Probably like a little broader, but yeah, like chemicals. But what are you into? Your name's William, right?
Me?
Oh, no, sorry. What's your name?
My name's Brayden.
Braden, sorry. Braden. So what do you like? What's your top area of interest?
Well, it's always kind of been science, because I've been fascinated by how things work, or just how things go together. So, yeah, that's kind of all really I have right now.
So trying to figure out, so like, let's put how things work, kind of broad. And I'll kind of put, yeah, we got some sort of formulas or something that we need to dive into. Yeah, what do we think about chemistry?
Just kind of how it describes what everything is made of, like in our world as far as, you know, I mean, I can be closest relations. My interest, I like to cook, and so there's like all kinds of things within that, and then I'm also a psych major, so great chemistry.
Yeah, so cooking, so right, I like cooking, so we can get into food science, right? You can talk about fat composition, different flours, right? Protein, starches, different ways to quantify it. Yeah.
I mean, I guess my understanding of chemistry is everything's made up of chemicals, of course, so it's the study of how everything interacts with one another and potential good things that can come out of it or bad things. I'm interested in hygiene. I've been a dental assistant for a while, so it's more so an applied thing in my brain of whatever I do here can have a substantial consequence to whoever I'm dealing with.
Yeah, so that's perfect, right? Dental. So let's think about that, right? So not only are we thinking about the chemistry of the teeth, right? How do different things interact with teeth? we'll just have like a very basic overview with acids and bases, kind of talking about pHs, right? You can think about how that wears upon your enamel. But also, if you're in the medical industry, is anybody here going to be a nurse or thinking about being a nurse too? So kind of write the same thing. I'll put like nursing. So it's really important, and we're about to talk about all this, and you've kind of gotten a little taste in lab, but right, you have units of measurement, right? You have to give people medicine, and it might have a dosage, right? So many milligrams per kilogram, so then you would have to calculate, right? For your patient, you have to know the difference between micrograms, milligrams, right? Density, so all those little things come into play. Well, what else? What else are your interests? I'm hearing a lot of like what chemistry is, but like how can we tie it to everything, right? Because we're not just in this class, so like, oh, I'll study about molecules. It's like we want to think about, well, what can we do with this? So that's also, right, what I'm getting at, and where chemistry is tied into. And, you know, maybe you don't know it yet, but maybe you want a career in chemistry or science. Yeah. Yeah, so that's a big thing too, right? Getting into like, you know, what drugs are appropriate, like, you know, different psychoactive drugs, what is good to cross the blood-brain barrier, right? That's always a challenge for drug development. And then, you know, what are you trying to mimic? And, right, we could get into a lot of structure and function. A lot of those antidepressants are based around tryptophan. Yeah.
Radiation technician?
Yeah, radiation technician, exactly. So now we're thinking, right?
You have to operate the x-rays and the MRIs in the hospital.
Yeah, and so you might have to know something about isotopes too, and right, imaging, so that's good use. What else are we thinking?
I feel like general chemistry can go into a lot of things, such as like I used to work in a cabinet factory. We had paint cabinets. We knew what was around us at all times because I could go up in flames in my paint.
Yeah.
If I wasn't careful.
Yeah, and so that brings up like a really good point too, like anything from, so any painting, finishing, all that's organics, but you've heard like horror stories, right, of people, they mix chemicals while they're cleaning and then they make chlorine gas and accidentally die, right? So just knowing those little basics for cleaning, painting, that's all helpful. All right, what else? So we can touch on other stuff. So ag, no one's excited about big ag. So I only bring up big ag because I feel like my friends either do one of three things if you're a chemist. You either go to big ag, big pharma, or you teach. So I know a lot of people in agriculture, so that can be anything from like pesticides to, somebody said the word ammonia, right? So ammonia is really important as fertilizer bases. So all those things, so there's tons of money in there, or new pesticide development, blah, blah, blah. And then, right, we didn't even touch about geochemistry, so either we could get into the composition of rocks or getting into oil industry, right, how do they determine what sites are good, so chemistry is obviously related to that. And then environmental science, I mean, this could be anything from like, let's be more sustainable to, you could get into like law and environmental law and, you know, get into that. So that's a good connection. And then obviously any sort of engineering or materials, right, that goes into strengths and back to alloys or coatings. So all sorts of little bits of chemistry. And so, right, this graphic is also probably made by chemists. So obviously, right, chemists feel like their science is important, so they have it here as kind of almost the central science. And it, you know, does relate to a lot of sciences as well, of course. And we didn't even touch about nuclear chemistry and energy and all those good things. Energy. And yeah, I didn't put pharma. I should put pharma in there. Drugs. Yay, everybody likes drugs. Let's see. I should have said, I should have had y'all take bets on how long it'll take me to start talking about drugs, but anyways. And so I think all of y'all have a pretty good understanding of what chemistry is. So officially defined as the study of matter. Obviously, right, that's really broad. Matter is everywhere, everything. And so now we define matter. So anything that has mass and takes up space, and it can change from one form to the other. And so we'll talk about, of course, chemical changes, where we have a chemical reaction, where substances are used up and others formed. Of course, we'll later learn, right, it's more of atoms being rearranged. But we'll look at that. But I think, again, people were touching on that, right, some sort of formulas, compositions, but we have to get there. And then we'll talk about physical changes as well, where a matter does not lose its identity, but of course just changes its states. All right, so let's start with that. And again, this is probably a pretty basic refresher right now, but we want to make sure we're all on the same page. And we'll also just, discuss our three basic states of matter, so solid, liquid, gas. And so we have that matter can be, of course, classified by its state, solid, liquid, gas, based on its property. And so, of course, in a solid matter, particles are packed extremely tightly. And so I want you to remember, right, they still have vibrational movement. So they're still, right, vibrating a little, they're still moving, but they just can't move past one another, right? They can't slide past. And we could say, right, well, now we're adding energy. So if we add energy to this, then our molecules will start to move more. And so now let's say, and again, we can all think about water, because I assume we've seen water in all three states of matter. You start off with that ice, and you start adding energy to that process, right? Your molecules start moving around more and more. And so now they're closely packed, but can move. So they can slide past one another. And so, right, we could say that we have a fixed volume, but its shape, of course, can change. A solid, we'll say, right, fixed volume, fixed shape. And then, of course, right, you know what happens when you boil water. You keep adding more and more energy, and now they're not just sliding past one another, right? They're moving and bouncing around. And so now in gaseous matter, they're widely spread apart. And so I'll use the term that gases are compressible. So that's kind of their distinction. So they can expand to fill the room, right? You can compress them down. You can compress them all the way back down to a liquid, right? So you could take, so liquid nitrogen is just commonly abbreviated LN2. So that would just be liquid N2. And so I'm sure you've seen like those big tanks at the car dealership. And so that's all it is, right? Compressed nitrogen. You open up the valve, and out comes your gas. And so, of course, gases have, right, no fixed volume or shape. And so now these are just the words that kind of accompany those pictures with, again, some examples. And so, once again, just a reminder that they're still vibrating in the solid form. They just can't move past. And then, of course, giving us examples, right? Ice, aluminum, diamond, all those are solids. I'm sure y'all could go on and list a bunch. And liquids, right? Again, now we're saying that they are moving relative to one another, just able to slide past, but we still have that fixed volume, of course. You know that as you pour your water or coffee into different containers. And then gas, again, we have that term compressible, so that being our key there. Questions on that so far, states of matter? Feel pretty good? Probably a refresher. Okay. And so now we'll get into the classification of matter. And so now we want to break this down. And so let's kind of start with the simpler stuff. And so our first question is whether to ask ourselves, well, is it one type of particle or not? And so what it's really asking, right, is it several things, or is it just a compound or element? So that's your first distinction. And so let's just start with, well, what's an element? How do you know if something's an element? So we can't break it down, but then how do I know that? What if I really don't know? What's our cheat sheet? Where are the elements all found?
Periodic table.
Yeah. All right, so make sure you grab one. And I print these on cardstock so that you can keep them, forever and ever and cherish them. So yes, first step, right, especially if you're new to chemistry, and I'm assuming that y'all know nothing, you maybe don't even know, right, your elements. So yeah, perfect. This is just the place to be. So first step, right, maybe glance to the periodic table. Is it on here? Right, so then you can start finding, okay, well, we have carbon, nitrogen, oxygen, right? Those are all elements. Sodium, right, notice that that's not just table salt, but that's just Na, so we'll get into, right, all the compounds. But yes, found on the periodic table, cannot be broken down, so all good definitions. So we'll write that. So cannot be broken, so found on our table. And so we'll look at some more elements because there's a few tricky things. And so let's look. I do want to show you, so this is another periodic table that's helpful, and I'll reference it at other points throughout the year. So you can just find this online, ptable.com. It's kind of nice, right? You got this interactive periodic table. Oh, as I say this now, it doesn't want to. There we go. Click on properties, and it shows like the Wikipedia page. So you can always pull up the pictures, which is kind of nice. I thought it used to hover and show the pictures, but. All right, so we'll go back and forth. So yeah, first step is identifying. And so let's look at a few, I call them oddities, but they're things that maybe you don't think that they're an element, but they're an element. And so let's start off with our diatomics. So does anybody know what this means, diatomics, this phrase? Okay, nobody knows. That's perfect. And so a diatomic is just an element that is bound to itself. And so this is how it exists in its elemental form. And so again, let me break this down a little bit further. Well, let's first say which are our diatomics, and then we'll get into kind of why they are diatomics, but we'll kind of revisit the why a few times. So there are 7 diatomics, and the only odd one is hydrogen because it's off by itself. And then the rest kind of make a little 7 pattern over here. So we have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So notice, right, those are going to be, and these are called our halogens, which we'll come back to that. So kind of introducing a lot of terms. So this is our halogens. We'll learn that they're pretty reactive. So this is kind of like our first clue. And so what does this mean? And so again, all I'm saying is that, oops, in its elemental form, in order for it to be stable, it has to bind to itself. So we have hydrogen, and again, I'll write them all out. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And so notice it's their atomic symbol and a little 2 here, again showing that that's how it exists, right? So you won't have hydrogen, just lone hydrogen, atomic hydrogen. So this would be called atomic hydrogen. And this does not exist normally. Well, we won't get into where it does exist. It might exist on like some star, but does not exist on Earth. So it has to, and it has to make a bond, which now I'm kind of jumping too far ahead, but we'll revisit why they are like this. But just accept for now that these are diatomics and they are found like this. And so now let's look at a few others. And so we have our diatomics, but we also have substances that are called allotropes. So allotropes. Has anybody heard of allotropes, that term? What do you know about diamond and graphite? Know anything about them?
They both have carbon elements in them.
Yeah, so they would be examples of allotropes. So let's pull up Wikipedia for this. Oh. So.
If you compress carbon really with a certain amount of pressure, it forms a diamond.
Exactly. And so that's the point that we want to make, right, is that they're completely made out of carbon. So they're both elements, right? So now we're saying that graphite and diamond, not only are they elements, but they're also different forms. And so let me pull up the actual article about the allotropes. There we go. Allotropes of carbon. So carbon is pretty famous because it has a lot of well-known allotropes. And so we can look at our picture here. So this is diamond. Notice it's in that tetrahedral form, repeating. Again, all carbon, so repeats, repeats, repeats. So that's what makes it really strong. Now if we compare graphite, so graphite, right, you write with graphite. And so you can write with graphite because these bonds here, these intermolecular forces between the sheets of graphite are pretty weak. So it just shears off. So you can write, and again, right, just appreciate the difference in structure, how that leads to completely different properties, but still completely carbon. And then other famous ones are going to be this C60 right here. So this is the buckyball, and so that was invented at Rice University, and that of course led to all the nanotubes being made. So that's H down here, so that would be the nanotube structure. And obviously, right, there's more down here, not listed. And so allotropes, then we can define it as just different, if I could spell, geometrical arrangements of the same atom. And so again, right, these are all elements, but we can have, right, all our carbon allotropes, so diamond, graphite, nanotubes, etc., C60. And again, right, this is not definitive, but the point is they're all made out of carbon. They're just in a different geometrical arrangement. Anybody know any other famous allotropes? Like the other bet, how long does it take me to talk about war? Don't you love chemistry? So the other allotropes that are famous, which everybody likes, for better or for worse, are the white phosphorus, red phosphorus, so all the phosphoruses. And so let's pull up the allotrope article again. So here is white phosphorus, so toxic. I mean, all the phosphorus are pretty toxic. And then here's red phosphorus. And I think this is another violet phosphorus. So again, just different geometrical arrangements of phosphorus. And then we'll look at one more, just because this one's kind of a funny one. So sulfur is actually an allotrope. And so this is the correct structure of sulfur. So you don't normally see it represented like this, but you might see some people write the formula for sulfur being S8, which again refers to this weird 8-membered ring structure that it makes. All right, so I'll add under there. So we have phosphorus. And these are just, again, examples, right? So white versus red versus violet. We have sulfur, which is S8. And, you know, again, you can go on and find other allotropes. So this is not an exhaustive list, but just kind of the main ones. All right, does that make sense for elements? So basically, right, it's on the periodic table, but then don't get confused by these special cases. So again, our diatomics, still considered an element, and all our different allotropes, still considered elements. All right, so now let's go back to, well, what's a compound? So now that's kind of our next easiest thing to define. So what's a good definition for a compound? Does anybody have an idea? So a compound, yeah, a mixture of elements. That's, the word mixture is kind of, but what's the key with the compound? Yeah. Yeah, so still kind of the same idea of like mixing element or atoms, but there's something key that we're missing.
Would it be that it's on the molecular level rather than the atomic level? Because it's multiple elements combined?
That's not like what, that's not necessarily what I was looking for. There's like a key definition. That's part of it. So, right, it can't just be separated by like physical means, right? So you have to have chemical separation. So that distinguishes compounds versus mixtures. But what would the compound, because, right, we don't just have a random mixture, do we, of atoms? So what's the key there? And maybe you can even list off some compounds and it'll come to you. What are some?
Is it like it's a measure, like for that picture of H2O, so it's like 1 oxygen, 2 hydrogen?
Yeah, so what the word I was getting at is like a defined chemical formula. So yeah, defined chemical formula. Yeah, and so I like that, right? So then you start thinking, okay, H2O, right? And it's not just a mixture of hydrogen and oxygen atoms at any random ratio, right? It's a clearly defined, like you said, 2-to-1 ratio. And that's also, you know, again, different from our mixture, right? Because our mixture, same thing. You can change the ratios, that just kind of changes the concentration, but that's different than having a defined chemical formula. And so what compounds do we like? Any other compounds we can think of?
Sodium chloride.
So sodium chloride, so NaCl, good old table salt. What else do we like? carbon dioxide, sodium hypochlorite, so bleach. Carbon monoxide. Other thoughts? Glucose. There we go. I was wondering when the larger ones would come in. Come on, no druggies. Where's the aspirin even? Aspirin, cocaine. All right, other molecules that you want to list off? We could go crazy listing molecules.
I'm not sure what the ones are, but that material and fire extinguishers?
I don't know, because sometimes they use CO2. I don't know what the other chemical is, the ones that are powder. I'd have to look it up.
Something in fire retardant, like that's dropped from.
Oh, yeah, the red stuff.
Yeah, the red stuff, that's from fire.
Yeah, I forget what chemical is. Fire retardant. Phosphate. Huh?
Potassium hydroxide.
Potassium hydroxide. Hydrogen peroxide.
Hydrogen iodide.
There we go, some organics. Jeez. And I'll add on there. Actually, I wouldn't put Phos-Chek under there, because I think it's not a distinct chemical from what I'm looking at. All right, we'll look. So actually, I will put it under. So now we'll go to mixtures. Oops. And so now we have two different mixtures. So we have homogeneous or heterogeneous. And so heterogeneous just means that like it's not uniform. And so I always think of like, you know, chocolate chip cookie dough ice cream or something, right? Where you got big chunks of something, or if you take some sand, salt water, and it's got like layers of sand in the bottom and salt water on top, right? That would be heterogeneous. Why something that's homogeneous would be, you know, tea, Gatorade, basically uniform throughout. And so with that, I will put Phos-Chek probably through a uniform mixture. So that's the red stuff. But from what I'm reading, it's like phosphate and sulfate salts and clay mixtures. So yeah, that would be a homogeneous mixture because it looks like one big red powder. And so let's go back to heterogeneous mixtures. So what are some examples of heterogeneous mixtures? And you could use food too. So chicken soup is a good one, right? You got different chunks. What did you say, sorry? Yeah, peanut butter jelly, especially if you're doing like a chunky peanut butter. So any sort of cookie dough. Yeah, that's a good one. So asphalt or concrete mixtures, right, with the different rocks. Any other thoughts? I'll put salad dressing. That's the other like common one that everyone says. And then what about homogeneous mixtures? Yeah, so juice, got sugars and water, all sorts of different things. Vaccines. Yeah, I think that could work. I like a homogeneous mixture. So seawater, yeah, just as long as, right, there's no like sand in it.
Gas and water solutions.
Yeah. So gas, water, so it could be like soda maybe you're thinking, or
Like muriatic acid.
muriatic acid, yeah. And then I would also put like, oh, sorry. What did you say?
Picrete. Basically, it was a type of made-up element that was developed back in World War II where you take wood and you take ice and mix them together, it created picrete.
Ah, I'm not familiar with
It's a real name.
Pycrete?
Pykrete, I believe.
Okay. Pycrete, cool. And then the only other thing I was thinking of is like, again, other drugs and stuff. So the specific one I was thinking of is like Alka-Seltzer, because that one has acetaminophen and other stuff in there. So it's like a mixture of different chemicals. All right. Any other thoughts on separating our substances? Do we feel okay about this? All right, so let's finish up kind of the rest of this, and then we'll probably take a little 10-minute break or so. And so again, these are just kind of words to recap it. So like we said, right, we had our pure substance, either an element or a defined compound. Again, our important thing is that we could find a formula for our compound. And then anything else is a mixture. And so then kind of the next thought with mixtures is also how you separate it, because obviously that's a big part of chemistry, is how to separate it. So today, right, or Wednesday in lab, you'll do a little separation, just kind of get you a taste of it. And so here is just showing a simple method for separating a mixture. And so, right, this would be more for physical separation, like we were saying, so not a chemical transformation. And I'll first say, right, you would never do a distillation with an open flame. I don't know why this was in the picture, but you'd want to have a heating mantle instead. And so that would get your source of heat. And, you know, let's say you're just trying to separate out some salt water. So heat it up, obviously your water vapors rise. And then we have our cooling part here, so it condenses back down. And then we'd have pure liquid. And so you can distill, you know, any liquid really. If you needed to, you can, you know, separate out different boiling mixtures as well. And in industries, so how to make like fuel and stuff, they use essentially a large column that does the same thing, just on a much larger scale. So you have your low boiling stuff up top. You know, any gases tend to be collected at the top of these distillation chambers. And then down at the bottom, right, is going to be your diesel, wax, all your much higher boiling hydrocarbon mixtures. All right, so let's take a little break and then we'll go into units. So let's see, what time is it? So let's try to be back around 2:05 or so.
the date, I thought that this week was like the ending the week of like the, for the 8th. It's the week after. I was wondering if I could like take my final and stuff on that Friday.
Yeah, you
before
could probably
finals.
do that, yeah.
I think it's the 6th. Just
Yeah.
the 6th, okay. Thanks.
Oh,
That was,
yeah, don't worry about it with my class.
like, some of these things are being marked late for,
Yeah, don't worry about it. I have to go and change every due date before Blackboard stops, and even then there'll be hidden assignments that it's telling you got a 0 on. So.
I've already been getting that for this.
Yeah, I know. Everybody already has an F, so don't worry about that. That's why I say don't look at your Blackboard grade. All right. Do we all make it back? I realize I forgot to say when my office hours were, but basically my office hours are anytime. So best practice is, I guess, office hours are before or after class. So I'm available after this class every time. You know, we have recitation, and then that can just continue on to office hours. If that doesn't work, Tuesday, Thursday, so let's see, I have class from 11 to 1, but you can hunt me down before then. And then I teach lab 1:30 to 4:20 and 3:12, so you can hunt me down there. And then on Fridays, I will also be in 3:12, 1 through 4, so you can hunt me down on Fridays as well. Basically, just email me and set up an appointment. Or, again, hunt me down after class. Like, I'm around, I'm trying to be available to y'all. Does that make sense? All right, let's go to units now. Because if anybody will be needing to see me, it will be over units very shortly. And so first we'll talk about, well, you know, why do units even matter, right? Some of you were discovering in lab today, you know, why do we need to put mils or, right? You distinguish centimeters, milliliters, all that's important. And so let's look at this little scenario. And so this was a Boeing Delta II, and they were doing this launch vehicle, so it was trying to go to Mars in 1988. And so what happened is that, right, the two companies were not in the same unit. So it's always important to, right, state your unit and state it again. And so basically, right, the software that calculated the force that the thrusters needed was in pounds. And then the second piece of code assumed that it was in newtons. And so, right, mismatch. And so, of course, that was wrong. So, right, with the mishap in units, then basically I think it entered in too fast to the planet's atmosphere, and so it just burned up and broke into pieces. So, whoops, talk about a costly mistake. So, right, moral of the story, always, again, label your units. So that's why it's important. All right, and so let's talk about some other things. Of course, right, science deals with all sorts of things. So just for fun, does anybody know, like, the size of a human hair, kind of what order of magnitude that is? What do you think? Centimeters, millimeters, smaller than that? So it's on the order of micrometers. And so that's 1 times 10 to the negative 6 meters. But again, we'll get into all that. This is just kind of, you know, for fun, just kind of where are we? What about atoms? Do you know what size the atoms tend to be on? You could also give me 2 answers for this one. And so we could use, right, nanometers. So that's 1 times 10 to the negative 9 meters. Or sometimes in chemistry, they have this special unit, and it's this little A with a circle over it, and that's called an angstrom. And that is 1 times 10 to the negative 10 meters. So pretty small. And so again, you just see that as our kind of scale. What about an elephant? Like, how much does an elephant weigh? Yeah, tons, right? So tons, does anybody know what a ton is roughly?
2,000 pounds.
Yeah, 2,000 pounds. So, right, we can have, I think elephants weigh anywhere from like 2,000 kilograms to at least like 6,000 plus kilograms or so, or several tons. That's right, again, big units. And then, anybody know the distance to the nearest star?
Astronomical units, AUs.
Yeah. And then do you know how many light years?
It's like 2,000 or something above that. I don't remember. It's in the 2,000s, I think.
2,000 what?
600 something.
Like,
Acres?
well, it's not that many light years.
Uh,
So I think it's only like 4.35 light years or so. Yeah. So light years. But it is, so I have it as 37.8 trillion kilometers. So pretty large distance that we're talking about. Kilometers, hence why, right, they use light years for distance. And then, right, everybody knows that light years is the amount of distance that light can travel in a year. Makes sense. All right, so then kind of the whole point of that exercise was just to say, well, in the diverse field of science, right, we can look at teeny tiny things from the atomic scale, or we could be talking about, right, astronomy and light years and trillions of kilometers away. And so how do we deal with this? And so this is where, right, our metric system comes into play. And it, of course, is a little easier than our American unit, since everything just kind of depends on its prefix. And so each type of measurement has a base unit, so we'll go over all our base units. And then the metric system is based on multiples of 10, so pretty easy. And then we can create multiples of 10 by adding our prefix. So that's what we're going to be kind of focusing on probably for the rest of this class. So you want to grab this handout as well, if you didn't already. If people need the little, I call it our conversion kind of guide. Everybody grab one? Yeah, so we want to work on this. We'll be kind of going through this. And so first, let's kind of see, well, what are our base units? And so we'll get to it. So this is a special chemistry unit. So moles. So we'll go back to this and explain what a mole is. But you're probably familiar, right? Length is going to be meters. So that's our base unit. Mass is going to be in grams. Volume is in liters. And then we have temperature, which we don't really add prefixes to. And I will say that we should put Kelvin there, because Kelvin is the more important one. It's thermodynamically relevant. We'll go back to that. And then time, seconds, and then, of course, information, bytes, but won't do too much of that in this class. And so now let's go through this. And so the only thing is, I think there are two different ways to kind of think about it. And I think this way is kind of more confusing. And I'll go through with what I mean. And so it has these, what's confusing is this chart says quantity in one base unit. So what it's saying is how many, like let's say, teragrams, if you want to figure out how many teragrams in a gram, it would be 1 times 10 to the negative 12 teragrams in a gram. That's what this is saying. Does that make sense? And so what's kind of confusing for some people, and we'll go back to this conversion factor in a second, but this multiplier is different than the previous slide. So they're saying the same thing, just in different ways. And so now this is saying multiplier, so by the base unit. And so with this, I want us to take some time and write out our conversion factors. And so I'll show you, again, what we're going for. So we're going to take it real slow. And so conversion factors are really just relationships. So, we express it as a fraction to kind of help us with our dimensional analysis, and I abbreviate conversion factors with CF. But this is really just, right, a relationship. And so, of course, right, looking in our metric units, so we're saying, well, in 1 meter, there's 1,000 millimeters. And then we can write our conversion factors. But we'll go back to this. And so, right, it might be easier to think of, well, there's 12 inches in 1 foot, right? So that's also a conversion factor. So same sort of thing. And you can also write it or, right, there's 1 foot, 12 inches. So that's what that's saying. And so now let's look at the conversion factors. And I'll give you, again, a few more examples. And so if we want to do by the base unit, and I like to use grams just to kind of help me think. So then we're saying, right, we have 1 times 10 to the negative, sorry, I already screwed that up. 1 times 10 to the 12 grams make up 1 teragram, right? So that's by our base unit. We can flip that, of course. That's all that we're saying. So we can write it in a reverse relationship depending on which way we're going. Or maybe you like the negative number better. So going back, so now we're saying 1 times 10 to the negative 12 teragrams is equal to 1 gram. And then, of course, right, we could flip that, or 1 gram is equal to 1 times 10 to the negative 12 teragrams. So 4 different conversion factors, but they all mean the same thing. And so that being said, right, you may want to just stick to the positive conversion factors so you don't have to, get stressed out with negative numbers and remembering to put into your calculator and all that. But I'm just showing you the relationship. And so now let's do maybe one of our negative ones down here as practice. So again, right, this is saying by the base unit. And again, I'm taking grams. So if we do 1 times 10 to the negative 6 grams, right, that is equal to 1. Notice the symbol for micro is that weird mu. So make sure you add a U with the tail. So 1 microgram. Or we could flip that, right? Or 1 microgram is 1 times 10 to the negative 6 grams. Or maybe you're looking at this and you don't like the negatives. That's how I kind of feel. And so we can write it in a positive expression. So 1 times 10 to the 6 micrograms is equal to 1 gram. And of course, right, we can flip that, or 1 gram is equal to 1 times 10 to the 6 micrograms. So does that kind of make sense so far? So let's take a few minutes to try to write out the rest of the conversion factors. And I'm going to walk around and kind of see how we're doing with this. And then probably at the end, we'll go over and write it, or later on I'll fill it in so that you'll have a complete chart. But we want to work on this, just kind of getting our conversion factors, making sure that we can just lay it out appropriately. All right, so I'm going to walk around, raise your hand if you're really confused now and need help. And I'll make my way around. so just start with gigagrams, right? And just kind of copy the same thing, you know, by the base units, and then we're saying 1 times 10 to the 9 grams is equal to 1 gigagram. Yeah, 1 gigagram is equal to 1 times 10 to the 9 grams. And then you just, yeah, because it's just the base unit. And then you could flip it, because it's just the same thing, or you could try to figure out how to make it negative, if you like that. If you don't like it, don't even worry about it, type of thing. How are you doing? Yeah, so then this is like by the base unit, so 1 times 10 to the 9 grams, gigagrams, yeah, exactly. Yeah, and then just make sure once you get negative that you, yeah. And then this is the, is that like a little gram? Yeah, because you want to make sure that this is like grams for any base unit. Yeah, so that, because right now it looks like 2 big G's. Yeah. Yep, so 1 gigagram, 1 times 10 to the 9, that looks good. So those look good, and then now we have 1 times 10 to the 9. Yeah. So those, I think you got it. And how are you doing? And then, yeah, just make sure you're like writing some sort of base unit percentage thing, right? That would be grams, if you want gigagram. Yeah, or just any sort of like whatever base unit you like. I just like grams for some reason, but you know, you could do meters. How are you doing? Period. Positive. Yeah, how are you doing? Same thing, got it figured out. Yep. It looks like you got it. Yeah, I think you're a little left right now, because what we're trying to say is this is by the base unit, so we're saying 1 times 10 to the 9 grams would be 1 gigagram. So I would put, either that means like a negative sign, or you gotta put 1 gigagram and change that to grams. And then just make sure, because that's 6. Yeah. And then the same thing, make sure that you're doing 1 times 10 to the 6 grams is equal to 1 megagram.
So the one will always be like, so that.
Yeah.
And then here.
Yeah, if you're doing like the base units, or right, it could be meters or liters, right, so you got megaliters, you know.
Okay.
Yeah.
Yeah.
Yeah, and then just watch, because that should be like a capital G.
Oh, okay.
Yeah.
Okay.
Just
That makes
for the future. Yeah, so those look good too. And then you could think about, you know, putting those positive
Yeah.
you want, but
I just want to press.
yeah. Yeah, that looks good. Did you get it? Yep, so that looks good. Oh, just watch, because it's an 8 and that's a 6. 1%. Can't read that apparently.
But I'm like, as far as, labeling everything,
Yeah, and then you'd want to do like gigagram, megagram, or like liters or meters, yeah.
depending on what it is.
Right.
Okay.
Yeah, whatever
Okay,
your
what's
base
this?
unit is. All right. Good. All right, that looks pretty good. Just kind of going around, I think everyone was kind of getting, the hang of it, so fill in. So most people are pretty good at, again, copying the pattern. So, right, we're saying, so 1 gigagram is equal to 1 times 10 to the 9th grams. And I'll probably fill this in more explicitly later so you can have it all filled out with the negatives and everything. And then you went down, and I like positive units. I'll put 1 times 10 to the 9th nanograms is equal to 1 gram. And so just make sure as you do this, right, you use the correct symbol. And so, right, like tera is that big T, right, giga is G, so, right, notice gigagrams, or if you were doing, right, gigameters, gigaliters, whatever. And then mega, right, is big M. So some of the M's get confusing, right, because you have big capital M for 10 to the 6. You have milli M for 10 to the -3rd, and then, of course, micro for -6. And then, yeah, all these are lowercase. Obviously, I already pointed out the weird micro mu symbol. So I think that's good. And so I want to keep moving for now just so we can start kind of going with the next step, right? Because, well, what do we do with these conversion factors? That's great that we wrote them all out, but now we have to apply them. And so let's do, I didn't have any practice problems there. Let's start off with just a kind of more simple one before we throw in all the metric conversions. So let's start off with our good old, right, we have 12 inches is equal to 1 foot. And again, we can write this in 2 different ways. And so now we have our problem. And so now we'll say convert 56.7 inches to feet. And so let's go over how to approach this. And so I like to use this dimensional analysis method. And all it does, right, is you just kind of line up everything, and we can see how our units cancel. And so kind of, right, how we set this up is, well, we want to start with inches, so I'll kind of write that over, so 56.7 inches. And I usually just kind of put it over 1 as a formality. That kind of helps. And then, right, we know that we want to get to feet, so I need feet here for my units. So then the next thing is, well, we have 2 conversion factors that are appropriate, but which one do we want to pick, right, to end up with our appropriate unit, A or B there? So B, right? And so kind of the point of dimensional analysis is, so we'll set it up, and so you can know that it was the second choice, since now we write it up, our units cancel, and kind of the big hint was that feet was on top here, right? So feet was on our numerator, we wanted feet, so we need to be looking for something to get us to feet. And then, of course, once we put it in there, yes, inches cancels out, right, like it should mathematically, and now we can do our conversion. And I forgot to pull up my calculator. So here we go, and so now we can just punch it into the calculator, 56.7 divided by 12. And so now we can talk sig figs briefly. So that's coming and creeping on us. And so based off of our problem, so we have 3 sig figs here. And well, I know that we haven't explained what sig figs are. We will get there. But we can at least say, well, every number is significant. And so we have 3 sig figs here. Now, we'll later learn that any sort of conversion factor does not count. So we basically say it has infinite number of sig figs, right? Otherwise, we'd be down to 1. That really wouldn't make sense. And so now we want to report our answer to 3 sig figs. Calculator spits out this, and I need 3, so 1, 2, 3, so I'm going to go 4.73 there. So 4.73 feet. So any questions on kind of just the basic dimensional analysis setup? So right, that's why we took the time to write all your conversion factors. So hopefully all you're doing is referencing your conversion factors and plugging it in. So let's at least try a few problems. Let's see how far we get. So maybe just start with these. Yeah, let's just start with the first 3 right here, and we'll see how those go. So just kind of try them out, and we'll go over them. Is someone to put those 5 meters to kilometers on the board? Put it on the far board over there. Don't all volunteer at once either. No brave volunteers for the first one? Oh, you can do the next one. Oh, you ready to throw? Are you Isaiah?
Yes.
Okay. And then what's your name again? Sorry? Madison? Okay. Madison, you can do the next one if that's okay. Yeah, the grams to milligrams. Oh, show your work up there. Let's see it. Yeah, write it out. It's a nice answer, but let's go through it step by step just so we're all on the same page. And again, ask questions in here, right? No shame. It's a 100-level course. You know, it could have been a while for the math, so. Excellent. So, right, we can read over there. So we have what we started with, our 5 meters. And then, right, pick our conversion factor that's appropriate for going meters to kilometers. And of course, right, meters happens to be a base unit, so there could be some tricky stuff later. And then, right, just plugging in our conversion factor. So just make sure, right, you recognize that. All it is just a conversion factor and 0.005. Questions on that one? Again, ask now or forever be silent. Do you have a question on that, or?
I might ask you later.
Yeah.
My brain's going, oh, I went and got that was completely different to the conversion factor. I'm not sure.
Yeah, we can talk after
I use,
too.
like, decimal points, like.
Oh, yeah. That's,
So, like, the process of it's
I don't want to like discourage moving decimal places around or anything, but I'd probably try to get into a dimensional analysis gear only because for like stoichiometry and stuff, when you're doing multiple conversions, it may become more difficult to follow. All right, Madison, you want to put this next one up, 3 grams to milligrams. I think the marker's over there. Yeah. And you can, of course, always solve a problem anyway mathematically as long as it's correct. Excellent, so that looks great. So, right, we started with 3 grams, and we have our conversion factor. So, of course, make sure you get that right. So, of course, right, there's milligrams are tiny. So, we have 1 times 10 to the 3rd milligrams and 1 gram. Oh, I think you just accidentally wrote milligram on bottom. If someone wants to,
Sorry,
someone want to just erase the milli.
my bad.
No, it's okay. Nothing like being at the board.
Right.
Put some pressure. And then again, multiply across, so 3,000. Any questions on that one? And right, always do a little sanity check too. It's like, well, this is a bigger unit. We're going to a smaller unit, so we should have more of the tiny unit. And let's try this next one, and then we'll see where we're at time-wise. So 7 meters to centimeters. Anybody want to do that on the board? Let's have another victim. Let me move on. Yeah, go for it. Sorry, I blanked on your name. Rebecca. I need my cheat sheet for now. I'm hoping to at least learn your class, but I have like 60 students in my 200 levels, so I may never know them. Oh, your math looks, no, I was going to say it looks correct, but I think your final answer is wrong. But the setup looks right, because if we go through it, oh, you're standing in front of your conversion factor, so I can't see. Yeah, well, so let's go through it, because you have 1 centimeter is equal to 1 times 10 to the negative 2 meters, right? So I agree with that. I just think you like literally didn't punch it in right. Because if you punch in, right, 7 divided by, and this is a good time to practice, so 1 second E, notice it's EE on this type of calculator. If you have another calculator, you know, make sure that you practice, because your calculator, you need to learn how to use it. But yes, if you punch it in, you get the answer as expected, which is 700. So remember, right, you divide by negative exponents. That's the same thing as multiplying by the positive. So it was correct in your setup, but again, right, make sure you're punching it in correctly. And that's also why I encourage positive exponents. So, right, you don't have to remember to punch in that negative too. But. And of course, right, you could have used the positive conversion factor. So 1, yeah, 100 centimeters is 1 meter, right? That could have been another conversion factor. Either way. Questions on this one? So we still have some time. So now let's see if you can tackle this 60 milligrams to kilograms. And kind of what's a little different about this one than the previous ones? How can you tackle it? And there may be more than one way to solve it. So I'll let y'all kind of think about that for a moment. You want to have a calculator. It doesn't necessarily have to be a TI-83. That's just what I have the virtual machine as. Yeah. Do you want me to get you like a calculator? Because I could also, like the school has a few to borrow. Yeah, that's fine. Yeah, so people that are like panicking right now, so if you may need to buy a calculator, right? That could be an option. You could use your phone calculator. It's just like you have to let me know for an exam because I'm going to probably place you up front if you're using a phone calculator, so I know you're not like sneaking off to the internet. So that's an option, is phone calculator. Or the school has a few calculators to lend out. So I could go grab some right now, and if people want to play with that. But I would say, right, get a calculator early so you can play with it and practice it. Because I can only just model, right, the TI-83. You could also use a virtual machine of TI-83. But that's what I have. But again, any other thing you need to practice how to enter in exponents on your own. So it's good to get yourself a calculator that you like and familiarize yourself. All right, so I may go run and grab some calculators while you think about this for another second. Anybody want a calculator? I have one extra. Okay. So before we run out of time now, so did anybody figure out at least what's the difference or maybe how to approach this? Any thoughts? So what's the problem? Did y'all solve this no problem? So Isaiah, looks like you got, or let's just first talk about, well, how'd you approach it? Because I think that's the first problem for a lot of people is they may not know how to start it. So what did you do?
I just kind of looked at the difference between the multipliers of kilograms and milligrams.
So that's one way to do it. So this is a more, I would call like advanced method. So basically what he's doing is you can compare, right, your multiplier units, and then you essentially divide, right? So you get a 10 to the 6 difference between them. So you're saying, well, 1 times 10 to the 6 milligrams is equal to 1 kilogram. So is that what you determined? So that's one way to do it. But that being said, if you're not that comfortable with math or, maybe this seems too confusing, I would encourage you to do what's called, I call it my 2-step method. And we might rush through it right now, and then we'll probably revisit and practice on Wednesday. I just at least want to show it to you. And so what I would want to do is, and kind of the difference in what you should have recognized maybe, is these all involve your base units, right? So that feels a little easier when you're starting at your base unit. So in this case, if we don't have a base unit, let's go to our base unit. So we're going to go milligrams to grams to kilograms. So it's more of like a 2-step conversion, but that way, we feel comfortable. So now we'll do, 60 milligrams, and so now let's get our conversion factor for grams to milligrams. So there's 1,000 milligrams in 1 gram. Now we can go from grams to kilograms. So this is, right, just conversion factor, second conversion factor. So now I have 1,000 grams in 1 kilogram. Now our units can cancel, right? Milligrams, milligrams, grams, grams. We're left with kilograms. And so now we can just multiply this. across, so 60 divided by 1,000 divided by 1,000, which notice, right, dividing that twice is essentially the same as that 10 to the 6th factor, and so it all comes out the same. So you should have gotten 6 times 10 to the negative 5th kilograms by whatever method. Well, like I said, so I think we're out of time. I wanted you to see this, but on Wednesday, we'll keep practicing these conversion factors and making sure that we feel really good about it. And then, of course, if you have questions, right, see me now for office hours. I don't know if there's a class after us. If so, we might have to like migrate and reconvene. Otherwise, we can just kind of stay here and you can ask me questions until you're satisfied. And then, of course, let me know if you need anything else. Make sure you, again, register for lab lecture recitation. And on that note, I will stop the stream here.